right. Yesterday was just the quiz. We did have a little bit of homework that we're going to go over today because I think it's quite important. Page 27. So if we have you just have to write the net ionic. If you want to write the whole thing, just, yeah, it's optional to write the whole thing. So this last one out of these questions here, if you recall yesterday, we were looking at choosing between the precipitation equation and the solubility equilibrium equation. Okay, and the first ones were kind of obvious. It's like the net ionic equation that occurs when we mix two things. If we're mixing two things, we're looking at creating a precipitate. Mix two things, make a precipitate. The next one, the next one was also pretty obvious because it says molar solubility and it says KSP. So anytime it talks about the solubility or it talks about the KSP, you know you're going to use the solubility equilibrium equation. In our third one, this one was a little bit trickier, but we were told that we had AgNO3 and we were titrating Cl with the AgNO3, which means that we are mixing two things, yes? And when we are mixing in this unit, we will be looking at precipitating. So if you mix two things, you're looking at the precipitation equation. Okay, if you're looking at KSP or solubility, you're looking at the solubility equilibrium equation. The very last one is a little bit trickier. Oh, no, it isn't. Why isn't it tricky? I thought it was tricky. Because it gives a KSP. Now, it is possible that this question could have been phrased without a KSP value because you actually have a table of KSP values. So you might be expected to go and look it up. If it didn't mention, if this question did not mention KSP, anyway, we see the KSP, therefore it's the solubility equilibrium equation. If the question did not mention KSP, you know it's not the precipitation equation because you're not mixing two things. Oh, also, it says a saturated solution. That's another clue. That you'll be using the solubility equilibrium equation. Because in order to have that equilibrium, the solution has to be saturated. If it is not saturated, you can't have the back and forth between the solid because there wouldn't be any solid there. It would all have just dissolved. Okay? So saturated solutions give us an equilibrium, so you're going to use the solubility equilibrium equation. If you have any room left whatsoever, so much, beautiful. Maybe in that little gray line down there, could you please write the solubility equilibrium equation for this question? Where would your solid go? Left or right? Left. Who is the solid? CaCrO4. Make sure you put your states. What kind of arrow will we use? One way or two way? Two way. And then we simply write our ions Ca2 plus, aqueous plus CrO4, 2 minus aqueous. This equation then allows us to write what kind of thing? The KSP. So from there, we could write the KSP. What would our KSP be? Yeah, concentration of calcium times concentration of chromate. Excellent. Now here's a quick question for you. If we have a saturated solution of this calcium chromate, what that means is that we took some calcium chromate, we dumped it into solution, and then we stirred it around. Yeah? So what we did is we took some CaCrO4 solid, and we dumped it into solution and we stirred it around. There's going to be some solid CaCrO4 at the bottom because it is saturated, but there will be some ions in the solution. What should the ratio of the ions be? 1 to 1. So if you want to know the concentration of the chromate, let's make the concentration of the chromate equal X. What would the concentration of the calcium be? Also X. Yeah? And then we're given a KSP, 7.08 times 10 to the minus 4. Yeah? And so then you could figure out X, and you know what? You just solved a KSP problem without even really knowing how to solve KSP problems. They're really not too bad. It's just, you'll find when we get to the end, there's a lot of different types, and it's easy to mix up which one you're doing, which is why we spend a lot of time saying, which equation do you use? Because that'll get you started off on the right foot for like this half and this half, and then we'll look at distinguishing those other ones as well. Okay. Okay, now, some of you did question 1 on this page already, so you already have a preview of what's coming up. But today we're just going to talk about the value of the the value, how big it is. I don't know what the word is for that. The how big it is of the solubility product constant. If you have a smaller KSP, what does that tell you about the number of ions? Yeah, because KSP is equal to the ions times the ions. So a smaller KSP means we have smaller ion concentration. Does that mean that more can dissolve or less can dissolve? Less can dissolve because we've got less in its dissolved form. Yeah? And if less is able to dissolve, what can we say about the solubility? The solubility is lower. Smaller. Now, because they're squared terms, if you've got a 2-to-1 ratio and, things like that, we can only really truly compare KSP values if we have the same ion ratio. So if we are looking at compounds where when the salts all have the same ion ratio, you can use this method to compare their relative solubility. So for example, in Ag2CO3, how many Ags do we have? In Ag2CO3, 2. How many CO3s do we have? 1. So we have a 2-to-1 ratio between the ions. Yes? How about barium and fluoride? A 1-to-2 ratio. And how about lead hydroxide? We have a 1-to-2 ratio. Yeah? So what that means is that the actual formula for calculating the solubility is the same for each of these. Let's just take a quick look at a couple of them. Let's do our Ag2CO3. Gives us Ag plus, 2Ag plus, sorry, plus CO3, 2 minus. And if we say underneath these, we are going to put the concentrations at equilibrium. We're not bothering with the initial concentrations because they're all 0. And because this guy is a solid, it doesn't really have a concentration. Does that make sense? Okay, well, so if I say 1 molar NaCl, is there really any solid NaCl in the solution? No, it's all dissociated, okay? So if I say the concentration of Ag2CO3 is 0.002 molar, that means 0.002 molar is dissolved and everything else is solid, okay? So if we say, let X be the concentration of Ag2CO3, then I can put an X down here. So that would be like my 0.002 molar. How much Ag plus would we get? We would get 2. So we would have 2X. And carbonate, we would have how much? X. And so then if we write our KSP expression, so KSP for this one is concentration of silver squared times concentration of CO3, 2 minus. If we throw our x's in there, you get 2x all squared times x, which is equal to 4x cubed. Yeah? So I get 4 from here. 2 squared is 4. And then I have an x squared times an x. So that's our x cubed. Okay. Now, if I do the same thing, let's do the same thing for barium fluoride. Okay, so let's take our barium fluoride, BaF2 solid, in equilibrium with Ba2 plus aqueous plus, I keep forgetting my states. I've been doing acid-base for too long. There we go, that's better. 2F minus aqueous. And if we let X equal the concentration of BaF2, could you guys fill in this equilibrium concentration row for BaF2 just like we did for the silver carbonate? What would go under the BaF2? X, and we're going to put it in brackets because it's a solid, okay, because it doesn't really have a concentration, but it does, okay. And what would go under the barium? X. And what would go under fluoride? 2x. And then if we do our KSP, Ba2 plus, F minus, squared. Barium is X. Fluoride is 2x, and then we need to square the whole thing, which again means we're squaring the 2, which gives us 4. And we've got x squared times x, which gives us x cubed. So in both situations, because we have a 2-to-1 ion ratio, the formula for KSP works out to 4x cubed, where x is the concentration of the 2-to-1 compound. Yes? Okay, so this is for a 2-to-1 compound. It works out to 4x cubed, where x is the concentration of the thing, whatever it happens to be. Okay, for a 2-to-1 salt. And what that means is that KSP directly relates to the concentration in the same way for each of those salts. So if one is bigger than the other, that means it has more ion concentration because the math is the same. So we can compare these directly. We can say, now relative solubility, actually we should make sure we have this defined. Their relative solubility is their relative maximum concentration. solubility is maximum concentration. The higher the concentration, the more that can dissolve. Solubility is the amount that can dissolve. So the maximum amount that can dissolve is the maximum concentration. The maximum concentration is the solubility. Those all mean the same thing, okay? So out of those three compounds, which one is the most soluble? We have a 10 to the negative 12, we have a 10 to the negative 6, and we have a 10 to the negative 16. I'll let you finish writing and have a chat with your neighbor about that. Which one is the most soluble? Well, which one can we eliminate right off the bat? Because it's right in the middle. We can eliminate number 1 because it is in the middle, yes? It's not going to be the most soluble. It's not going to be the least soluble. It's 10 to the negative 12. That's in between 10 to the negative 6 and 10 to the negative 16. If the KSP, which remember is the concentration of the ions, right? It's proportional to the, actually, that was fun. Okay, I've almost fixed my pen, almost, but not the pen, the program, but I don't have an eraser. So I need to fix that next. It seems to work great though, unless I'm trying to use the eraser that is no longer functional, and then it goes funky, but maybe not. There we go. Okay. Okay. What just happened? Where did everything, oh my God. Okay, hang on. There we go. Okay. So sorry. No, that's not where it's supposed to be either. Z. To normal. So is something more soluble? This shouldn't be an equal sign. This should be a proportional sign. Do you guys know the proportional sign? Looks like a fish. Do you know that symbol? That means is proportional to. That means as the concentration of ions go up, the KSP goes up. So when we say the concentration of the ions is proportional to that's a really handy little symbol because is proportional to is a lot of letters. Yeah? is proportional to KSP, that means now I'm trying to erase again, and that's not working. As the concentration of ions increases, KSP increases. It means there is a direct relationship between them when you put that like that. Just so you know what it means. Yeah, just in there is great. Thank you so much. Just so that you know what it means when you have a different sort of proportionality. If you had, are you guys familiar with like gravitational force? Okay. And if you're not, force is equal to GMM over R squared. Does that look familiar? If you've been in physics? Yes? And if you haven't been in physics, you can just ignore me. You can be like, okay, this is lovely that you're talking about proportionalities and stuff. Well, what that means is that force is proportional to mass. These are our masses. It's proportional to each of the masses, right? Because if the mass gets bigger, the gravitational force gets bigger. That's why if I drop this pen, it falls towards the earth and not towards me, because I have a smaller mass than the earth. However, r is the distance between those two objects. Okay, so that's the distance between the two objects. And the force is proportional to 1 over r squared. So what's going to happen is that as the distance increases, the mathematical relationship is going to be that the force gets smaller, and not just smaller 1 over x, it's going to go 1 over x squared. If that made no sense to you, you can just ignore it, and you can just know that when I say ions is proportional to KSP, that means as the ion concentration increases, the KSP also increases. That's all you really need to know, and you can just ignore this, okay? So out of these things, which one has the highest KSP? Biggest KSP? These are negative exponents here. So this one here is the largest. And this one here is the smallest. So which one has the highest ion concentration? I'm going to put them in order from KSP biggest to KSP smallest. So that's our biggest to smallest. Which one is the most soluble? First one. This is the most to least soluble. Does that make sense? Okay, it's got the least ions. Okay. And this one is the most ions. Do you need to be able to sit here and explain all of that? No, you don't. You just need to know that the bigger the KSP, the more soluble it is. So that is the, out of all of this, the bigger the KSP, the more soluble. So let's put that just down here. That is your takeaway message. The bigger the KSP, the more soluble. You can only do this, though, for compounds that have the same ion ratio. The good news, this usually comes up in multiple choice questions, and they will all be compounds with the same ion ratio. They're not going to give you other ones, because once you start throwing in other things, the math becomes different, and you would have to do all the math for each of them. So that would be like a really big, long written response question. And those are rare. Okay, so pretty much if you're given it in a multiple choice or even in a written response, you can you'll just be asked, it'll be like a 2-mark question or something, putting them in the correct order. You know what I mean? And they will be the same ion ratio. So you don't have to worry too much if it's not. Comparing the KSP values to determine relative solubility works only for compounds with the same ion ratios, which is what we just said. So you could compare these 3 guys because we have a 2-to-3 ratio, and we have a 2-to-3 ratio, and we have a 3-to-2 ratio. It doesn't matter whether it's 2-to-3 or 3-to-2. Those are the same. Okay? The order of the 3 and the 2 does not matter. For the same reason as in the previous question, the order of the 2 and the 1 did not matter, because the formula ends up being the same for KSP. The order of the numbers does not matter in the ion ratio. You could compare silver chloride, calcium carbonate, lead sulfide, because they are all 1-to-1. Could you compare silver chloride, calcium hydroxide, and manganese phosphate? No, cannot compare directly. Okay, so for example, this guy here, this is going to be KSP is going to equal x squared. Oh. For this one here, KSP is going to equal 4x cubed, and that's going to be KSP is equal to 3x all cubed times 2x all squared, which is going to be 27x cubed times 4x squared, which is going to be 108x to the 5th. Don't worry about how I got those numbers, but just be aware that you get a formula that looks like that. Don't worry about the numbers there, okay? It's big and it's ugly, but you got a different calculation for each one, so it would be like comparing apples and oranges. Okay, writing KSP expressions. It's really easy, but mostly you need to show all your work, just like everything. Show all your work. Each step is worth 0.5 marks. Okay, so if you're doing KSP, remember which version of the equation are you using? If you're using KSP, you're going to be writing the SEE, the SEE, solubility equilibrium equation. So you will write, and this is also known as the dissociation equilibrium equation, but we usually call it the C because that's nicer sounding than the D. I don't know. I think the C because you see the answer. Huh, no. Anywho, do not skip this step. This is worth 0.5 marks. Write the KSP expression. Don't skip this. What is the KSP expression for this one? KSP is equal to x squared, but before we put in an x, we have to put the concentrations in. So Ca 2 plus and CO3 2 minus. So this is the KSP expression, and the KSP expression uses that with the thing in there. Yes? So if you were told to write the KSP expression for MgOH2, the first thing you would do is you would write the C. So step 1, write the C. Step 2, write the KSP expression. So nothing weird there. Just make sure you show all your work. You will be able to, now how many of you did question 4 yesterday? Yay, most of you. We can go over it then. Wonderful. All right. So you are going to write the appropriate net ionic reaction, either the precipitation or the solubility equilibrium. And if you have not done it, don't write the answers down. The answers are in the workbook, but you can like sort of listen to it. You'll forget about it in a day, and then you can do the problems, you know, on the weekend, maybe on Sunday or Monday. Okay, because you guys have a long weekend this weekend, right? There's a Pro D day on Monday. Okay. So write the reaction that occurs when we have NaCl and AgNO3, and those two are mixed. Are we going to use the precipitation equation or the C? Yeah, we have two things that are mixed. When you see that word mixed, it's going to be the precipitation equation. Perhaps later you'll have to do the solubility equilibrium equation, but you should do this first. Okay. And does it say anything about KSP or solubility or saturated solution? No. So it is the precipitation equation. What is the net ionic equation for NaCl plus AgNO3? If we pair up NaNO3, is that a solid? No, because sodium is soluble with everything and nitrate is soluble with everything. I'm going to keep harping on that until you do actually know those ones by heart. Okay, hopefully you already have a slight sense that those are always soluble. So that is not our solid. AgCl, you can look that up. It says a reaction occurs, so we don't even have to look it up. We can just assume that we have a reaction. You can look it up to confirm it, but we have AgCl. So I would write Ag plus Cl minus gives AgCl solid, aqueous. Would it be okay to write Cl minus plus Ag plus? Yes. Yes. It would be weird Like I would never write it that way because it just seems wrong to me. Do you know what I mean? It'd be like calling me Spence Ms. I don't know. It just seems backwards. Like it's not like I wouldn't know what you were talking about, but it just seems odd. Yeah? Given the KSP for calcium fluoride is 4.9 times 10 to the negative 11, when 30 milliliters of calcium nitrate is mixed with 10 milliliters of 3 molar sodium fluoride, what is the value of Q, the trial KSP? Oh boy, that's confusing because you have a mixed with, yes, and you have a KSP, yes? What is the question asking you for? What is the value of the trial KSP? So that's the most important part. Yes? So you know for a fact you're going to be using the SEE. Someone in the other class asked me, shouldn't I be writing the precipitation equation first? You absolutely can if you want to, if it helps your brain, but you don't have to in a situation like this because they have already told you what the precipitate will be. It will be the calcium fluoride. Okay, so it is possible for this one. The C is all that is required. But you could write the PE if it helps you. So out of all those compounds listed there, if we are writing the C, which compound will be our solid? Will it be the calcium fluoride? Will it be the calcium nitrate? Or will it be the sodium fluoride? It's going to be the calcium fluoride because that's the one we have the KSP for. Okay, so it's going to be the calcium fluoride, CaF2, solid in equilibrium with Ca2 plus, aqueous plus 2F minus aqueous. Is good? Okay. Determine the solubility of limestone. We are given the KSP. What would we be writing? The C, yes. Thank you. Where does the solid go? Solid goes on the left. CaCO3, solid. One-way arrow or equilibrium arrow? Equilibrium arrow. Ca2 plus, aqueous plus Ca, whoops. Oopsie, what am I doing? I'm writing it wrong. Sorry? Yeah, that's great. I'll sort them out later. Does a precipitate form when equal volumes of barium nitrate and 0.2 molar K2SO4 are mixed? We got a precipitate, we're mixing things. So that's a precipitation equation. Where does the solid go? Solid on the right. Tell your partner, who is the solid? Is the solid barium nitrate? Is the solid K2SO4? Or is the solid something else? You're given a molarity for the barium nitrate. What does that tell you about it? That tells you that it is aqueous. When you have a concentration, it is aqueous. It is not solid. So is barium nitrate your solid? Oh, please. Barium nitrate is aqueous. Is it solid?
No.
No. Okay. Okay. Anytime you see a concentration given for something, that means molar means aqueous. So is the K2SO4 solid? No, because it is aqueous. Okay, we've got molar K2SO4, so the K2SO4 is aqueous. That means that our solid must be something else. Is going to be the? Yes, after those two are mixed, we will get a precipitate. Just like you did on your quiz yesterday, the precipitate happened at the end. I gave you the compounds first, and then you got a precipitate at the end. Who will be the precipitate here? Who is the precipitate? We have barium, we have nitrate, we have potassium, and we have SO4 2 minus. Who would barium go with? SO4. We would have to look that one up, yes?
No, not really.
Not really, because?
Because we know that NO3 is a salt of state.
We know that these guys are soluble, yeah. Although it does ask, does a precipitate form? So it doesn't imply that there definitely is a precipitate. So unless you happen to know that barium and sulfate are low solubility, you would have to look that up. I happen to know that barium and sulfate are low solubility. And so we would then write the precipitation equation. So we would have, where does our solid go? In a precipitation equation, solid goes on the right. BaSO4. Solid. What kind of arrow do we use in a precipitation equation? One-way arrow. Who goes on the left? Barium and SO4. 2 minus. Okay, last one. In a titration of 25 milliliters of 2.250 molar AgNO3, that was used to precipitate out all of the bromide in a 200 milliliter sample, calculate the concentration of the bromide. PE or SEE? Tell your partner what you think. Shockingly, it is the precipitation equation because we're looking at precipitating out silver nitrate. Or sorry, we're looking at silver nitrate being used to precipitate out the bromide. If you haven't already done so, could you please write that equation, the net ionic equation? You'll have to figure out who is the precipitate.
You have to make something that's like not low solubility with the AG.
So these are what we're starting with, the AgNO3 and the Br minus. Who is the precipitate when you mix those two things?
Sulfide. I mean,
Sulfide?
yeah.
What? No. We only have silver nitrate and bromide. Both of these are aqueous. What do we end up with? We end up with AgBr because really what we've got is we've got Ag plus and we have NO3 minus, because remember, anytime you were doing a complete ionic equation, for example, this is aqueous, so it will split up. Yes? Do any of those things mixed together give us a precipitate? Are any of those pairs of ions low solubility? Yeah, who? AgBr. So it's going to be AgBr solid plus what? What happened to our NO3? It's a spectator. So it's still, you could write it like this if you wanted to. Okay, or if it were me, I would be like, wow, that nitrate is irritating because it's not really doing anything. It's just hanging about, making the equation more complicated. So I would have a tendency just to write Ag plus Br minus. One-way arrow, because this precipitation equation gives AgBr solid. Aqueous. Is good? Okay. I want to see where we are at with everything. So many books. Are lots of people just doing it online? Anyone in here just doing it online? No. How come I have extras? That's okay. I must have miscounted. Alrighty. We want to. No. Oh, what the heck. Let's go to page 57. It's something I can teach you and you can practice on the weekend. Okay? Page 57, 3.3b. Page 57. We will do the rest of section 3.2. It's just that in the 15 minutes we have left, I can't really get through everything, so I'm going to assign you page 29 or whatever the heck it is, and then we'll do this so that you have something else to work on over the weekend, because otherwise it's a waste of 3 days. I know you're like, hey, wouldn't it be lovely to have no homework for 3 days? But that would just mean more homework for next week while you're, do you know what I mean? So let's just get a little bit done. This is easy. We actually already did this. We did this yesterday. Okay. So basically it involves, if we're given the solubility, which is the concentration of a saturated solution, In other words, it is the maximum concentration. So when you see solubility, it is concentration. And the unit is moles per liter. Okay, so the unit is molar. So solubility is the maximum concentration. The unit is molar. And this is a solubility to KSP. What kind of reaction are we going to be writing? What kind of equation? If we have a solubility and a KSP in there, we're going to be writing the C. Okay, so step one is write the C. And because we're working with KSP, we're going to write next the, anytime we're working with KSP, we have to write the KSP expression. Just like when we did Ka, we had to write the Ka expression. Okay, so this is going to be KSP is equal to concentration times concentration. You are going to need to find all the ion concentrations. In molarity. Don't worry about what a dump and stir type of problem is. I'll go over that next week because we're only looking at one type of problem here. Basically what it means is if I take compound AB2 and I put it into water, I dump into water. What's the ratio of ions? So I dump it in and then I stir it. How many A's do I get for how many B's? I get 1 A and 2 B's. That means that this is going to be X and this is going to be 2X. But you'll actually have numbers for it because you'll be given that number. Okay, and this value here will be X, but you'll have actual numbers. So you're going to find the ion concentrations, you're going to plug them into KSP, and you are going to solve them. So let's take a look at this. The solubility of BaSO4, remember that means the concentration of BaSO4 maximum is found to be 1.05 times 10 to the negative 5 molar. Calculate the KSP for barium sulfate. We're not going to worry about how you know this is a dump and stir problem. You can tell because you're only given one compound. One compound that you dump in and then you stir it. Okay? Let's just actually do the problem here. So what we're going to do is step one, we're going to write the C. What's up? Oh, okay. So where does the solid go? On the left, Ba, SO4 solid, in equilibrium with Ba, 2 plus SO4, 2 minus. We are going to put our, write the KSP expression. I'm actually going to do that down below. KSP is equal to barium 2 plus times SO4 2 minus. And the reason that I wanted to do that is because step 3, I'm going to find the ion concentrations in molarity. So I'm going to say, is this not plugged in? What is going on here? Okay, so barium sulfate, we're going to find our concentrations at equilibrium. What is the concentration of the barium sulfate at equilibrium? 1.05 times 10 to the minus 5. I'm going to put it in brackets because it is a solid, so it's not really, but it is 1.05 times 10 to the minus 5. And then what am I going to put for barium and sulfate? Same thing, 1.05 times 10 to the minus 5, 1.05 times 10 to the minus 5. And so instead of putting x in there and ending up with x squared, I'll put actual values, 1.05 times 10 to the minus 5 squared. And we get 1.1025 times 10 to the negative 10. So that's going to become 1.10 times 10 to the negative 10. Yes? Easy enough? Okay. So this is going to be part of your homework. If you are given something like grams per liter, we're not going to go through this whole question, but what would you do? You would have to turn it into moles per liter, and then you could solve it, okay? We're not going to do that whole problem because in essence, it's exactly the same, but you have to do a grams to mole conversion. And then of course, what happened here? Why is this so weird? There we go. And then of course, there's going to be some where you have it, you don't have a 1-to-1 ratio, you have a 2-to-1 ratio or something like that. And so you'll have to actually multiply the ion concentrations. So let's just assume that this worked out to 4.6 times 10 to the negative 15 moles per liter. It doesn't. That's just a pretend number. Yes? We would write our C. And this would be 4.0 times 10 to the negative 15. And this would be 2 times 4.0 times 10 to the negative 15. And this would be 4.0 times 10 to the negative. Where'd it go? Good gracious. 10 to the minus 15. And then your KSP would be Ag plus squared times concentration of S2 minus. And then you would have 8.0 times 10 to the negative 18 squared times 4.0 times 10 to the negative 15. And then you would solve it and la, 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 la. Yes? Was that too quick or was that okay? That was okay, because it's not very hard. Yeah, just take your grams per liter, convert it to moles per liter. Obviously, I didn't really do that. That's not going to be the real value, but that's how you would do it. So you can do Let's do the odd numbers. Okay, 1, 3, 5, and if you want to do the challenge, actually, let's do 1, 3. Yeah, that's okay. Yeah. Yeah, 1, 3, 5. And if you want to do the challenge, you can do the challenge. Ooh, it's got a titration in it. Okay.
What's the difference?
So this is page 59. Number 1, 3, and 5. If you want to do them all, that's fine. Okay, if you feel like that'll be better practice. And also page 29, finish. That's not very much. It's really very little. Okay, you got 3 days, 3 questions, and maybe a little bit on page 29, right? Yeah. Okay. Easy weekend for you. Whereas I get to mark 80 quizzes. I have not looked.
Okay, I went to like the embassy to
Uh-huh.
submit my passport.
Yeah.
Because I need it for student permit. Yeah, I just need it here, so
Okay.
I'll check the video
Perfect.
later.
Yeah, no problem.
Okay.
Perfect. Thank you. Oh, did you want to see your test? Yeah. And Owen, did you want to see your test? Not you, Owen. You, Owen. Nah. Okay. Thank you. That can just go inside. Perfect.